So welcome everyone to the session on supporting your AI development. Today we'll be talking about profiling your GPU or your models, visualizing your training, convergence, minimizing the training time, finding bugs in your actual architecture, and using all the cool tools that are available to make sure your model's running at optimum. As I was saying earlier, first speaker, CU, will be covering some of the ways you can interrogate or view the training, as well as some special tools for high-performance computing. And Wei will be covering how to profile and optimize your models. And he's published recent work in a very good AI journal where he's developed a very compact model. All right, so we'll begin with CU, I think, because his talk is the smaller one. CU, are you there? And you ready to share your screen?
Hi, Shex. Yes.
All right, whenever you're ready, go for it.
Hey guys. So for the next 10 to 15 minutes, I'll go through two programs that's very common in deep learning. The first is weights and biases, and the second is Docker. I'll devote less time for weights and biases because it's relatively straightforward. So it's basically a way to track your experiments, right? So when you run experiments, there are multiple metrics you have to keep track of. So has the model converged? What's the loss profile? And what are the images generated each epoch if you're using a GAN? And some metadata that's quite useful as well, such as memory usage, and identifying bottlenecks. So weights and biases is a uniformed website that allows you to do that. So it hooks up your training process to a website on weights and biases, which it'll just keep pulling data from your training process to visualize. So one very similar program before weights and biases is actually TensorBoard, right? So your program will keep running to a log directory, then you have this web interface to visualize the data. But weights and biases goes a step further by turning that into real time. So you have something running on the cluster and you can see the loss change in real time, which is quite cool. But unfortunately, I don't know if the links are still working. Let's hope it. Okay, I thought they were broken for a little bit. I guess, yeah, due to time limit, I'm not going to go through the demo too much, but what I'm trying to get at here is just you can visualize the loss functions as you go. And and even images. You can push images to the cloud in real time in your code. And I'll just quickly go through the setup. The setup is actually quite simple to add the program to your project. So you just import, so you just do pip install weights and biases, just one line. And there is a login. You register an account and you do WMB login on your terminal or cluster and just follow the prompt. And yeah, in your code, you just include just these two lines, weights and biases is set up. Then to log the numbers for visualization, let's say that that's something in your training process, every step you're logging the accuracy. You can just have that line, weights and biases.log, that'll send a push to the remote server. Then you can have those plots directly. Okay, so there is a lot of functionalities you can play with, but yeah, I'll just jump on to Docker now. Just highly recommend that you check that out and incorporate weights and biases for all your experiments. Okay, so the second thing I'll talk about is Docker containerization, which is a very important way to make your code reproducible. Whenever you work with AI, there are some very big issues you might have encountered with regards to reproducibility. First is you might have different machines at work, and your personal machine might run a different OS, and the cluster has a different OS as well. So the code might not be executable directly. And on top of that, you might have different versions of PyTorch installed on different machines, and all of them require different versions of CUDA. So it becomes a nightmare quite quickly, and you will have runtime errors when you transfer code from one machine to another. And worse yet, you might have results that are not reproducible. Maybe some version of PyTorch implements a loss function differently. So you have that silent failure, just give you different results, but you don't see it fail. Then there are dependency conflicts as well when you try to reproduce multiple projects, right? So if you're working on two projects that require two completely different versions of PyTorch, you can expect the dependencies to fight with each other. So you have to sort of have two machines to run them side by side. And then when you reproduce the code on a new machine, every time you have to set up the environment, which is really time consuming. So you have to remember the exact version of software dependencies you've used, sometimes even the order you've installed the packages, because those can matter sometimes. So it will be good to have a way to standardize that to make it more streamlined. Then the last issue is when you reproduce someone else's code from GitHub, some random AI model, if you run it as root access, as the root user, they can potentially modify your system without you knowing. So that's a huge security risk. But luckily, we have this program called Docker that standardizes all of those environment setup and runs the program in a very safe way. At a high level, Docker just containerizes or packages up everything you need into images. And by everything, I really mean everything. So it even includes an OS of its own, and of course, your application, your code, and all the dependencies it needs, and all the system tools and runtime. So here's just a simple application that uses some version of Linux and Python and database. Of course, you can add pretty much everything you need, because from the perspective of your program, that's a full computer. So yeah, down to the OS. So after having those images, we can run them as containers using the Docker application. So Docker will just create containers for your images. Each one of those containers are just like little virtual machines, right? And they use this technology called hypervisor to very efficiently execute instructions in a virtualized way. And what's amazing about this containerization is they have no interference with the outside world apart from just using the compute, right? So they wouldn't have dependencies on your operating system, and they also wouldn't make modifications to your operating system. So it's quite secure. And you can run as many instances of an image as you want because they are all virtualized. They don't have conflicts with each other. They don't write to the same directory, same file system. From the perspective of your app, that's an entire computer that it can use. And you can see how this also leads to a very scalable architecture for software development. So that's not too related to deep learning. Well, let's say that you have a web app or some application that doubles in user base. You can just spin up more instances of the same image, more containers to make your load capacity a lot higher. And yeah, it might be useful in AI as well if you're developing an AI web app. And to use Docker, there is usually 3 steps. So the first step is creating a recipe, which we call the Docker file. So it's just the text file that defines to Docker the exact steps it needs to follow to create the environment and configure the OS for execution. Then we use the build command to turn that Docker file into an image. So that's just sort of a blueprint, right? So the Docker creates following the instructions in your Docker file. And after that, you can just run those instances in Docker containers again, you can run multiple if you want. And there's no limit to the number of images apart from the compute you have. And the most amazing aspect of Docker, I think, is this thing called a Docker Hub, which is the official website to share your images. And most big companies actually share that software as Docker images. So some notable ones include Node.js and NVIDIA's CUDA, TensorFlow, PyTorch. So all of them ship their packages using Docker images. And what's amazing about that is you can actually use their Docker images as a starting point. You don't have to have in your Docker file how to install TensorFlow, how to configure GPU. You can just directly pull the image from TensorFlow, which should have that configured. And on top of that image, you can have your own configurations like installing additional packages, setting up the environment, copying the code to make your own image. So having that starting point is a huge advantage. And you can see how the entire software industry is sort of built on top of others' work, right? So that's sort of extends that philosophy. And after building that image, you can run it yourself. Of course, you can also share it with others on Docker Hub, right? So if you think your code can be useful to someone else, just share it so others can build on top of it. In fact, most of the Docker packages images are built on some lower level images. Maybe the TensorFlow is built on some lower level Linux version, and the Node.js, you can see they might have been built on top of other Linux versions. Some might be ARM64, some even PowerPC. Okay, that's quite interesting. And let's take a closer look at the 3 steps. So let's look at the recipe. So it's very simple and straightforward. So it just defines the steps Docker needs to follow to create the environment. Right, so that's our base image I've referenced from Docker Hub. So it grabs the latest version. That's not best practice here. You should always define a version, but just for demonstration's sake, I use the latest here. And here is your modification that you've made. So setting the environment variables, or you could also do pip install of your own packages. Yeah, just use the run syntax to add additional commands, and Docker will execute them. And a very important thing is to copy your code into Docker or your application into Docker so it has access to it. By default, these images have their own file systems, so they wouldn't have access to any code you have on your machine. But you can just do that by just copy everything into the Docker image. So now I'm copying everything in the current directory into this folder, and I set the working directory or the starting point of the container as that directory. So I have access to the code directly. So after defining the recipe, we can just use Docker build command, and we give it a tag -t. So that syntax so -t. So that's going to allow us to define a name for it. And we reference the Docker file as the recipe. And after that, so after typing that command, Docker is going to do all the configuration setup. It'll download that image, run all the commands, and we can use then we can use Docker run to run these images as container instances. Right. So here I just do Docker run, and that's the image I've built. That's the name, right? And that's the command I'm going to execute inside the container. And Python already comes with TensorFlow, right? And the main.py is what I've copied inside here. So I copy the code and set the working directory as that directory, so it'll have access to whatever file I have. And so if we're going to use GPUs for Docker, there's an additional step we need because Docker by default doesn't support NVIDIA GPUs. But NVIDIA has made this plugin to the Docker on the host system to have a GPU runtime. So just follow that link. It's just a 2-line installation. It'll add GPU support to your Docker. And now all you need to do is in your Docker run command, just highlight, just have this additional flag dash GPUs and pass all of the GPUs, and your containers will automatically have access to GPUs. And you don't have to make any modification on the container or image side. They remain unchanged. So it's a host side modification. And if you're using clusters, unfortunately, Docker is not installed because you may have noticed you need a lot of sudo access to run Docker. But luckily, we have this alternative, which is Singularity. But Singularity is less common than Docker, and there's less support, smaller community, and it has its own set of syntax commands as well. But luckily, it supports everything from Docker Hub. So to use a Docker image, you can just build a Docker image and push that to Docker Hub or some other hosts, and you can use Singularity to pull. Sorry, I forgot to mention Singularity is installed on pretty much every cluster, so you can just import them directly. And you can use Singularity to download the images from Docker directly. And you can use Singularity to turn that into a Singularity image. And you can run the images using Slurm. And the commands here is really just two commands, right? So we have the build command that turns a Docker image into Singularity. So just Singularity build and give it a name or a directory to store the build image. And here I'm referencing a Docker image. And that's completely fine. So if you look that up, it's actually hosted online. And to run it, so this sort of like Docker run, which is Singularity execute --mv is the one that exposes GPU to your image or containers. And here I'm mapping the home directory as well. So this is the starting directory of your image, and I'm mapping it to the current directory. So the image will actually have access to the current directory and can make changes, but only to the current directory, which we've mapped. And that's the image. Then we reference the image we've created above, then the same Python command main.py. So assuming that main.py is already in the working directory, so it'll just run without issue. And of course, we can wrap that in all the Slurm syntax. So as run and have a GPU, right? And have just running on the GPU partition with one GPU. So it works nicely with Slurm. And finally, you can have all of the Singularity stuff on inside Slurm as well. So this is your Slurm batch file, and you have your usual boilerplate. But instead of running python.py directly, you just run that using a Singularity container, right? So that's the image. So yeah, that's the image. Then we run the command inside the image. Okay, so just in conclusion, so when do we use Docker and Singularity? If you have small projects running, you may not need it because it's a little bit of overhead to set up. But if you intend to have your code shared or used by others, it's absolutely essential so they can recreate your code. And big companies often release their code as containers like StyleGAN3 or Stable Diffusion. So that actually makes it a lot easier to reproduce their work on your computer. And a lot of programs actually require root access. So it's best to run them in containers so they don't make modifications to your system, right? So like StyleGAN3 uses some custom CUDA plugins and C compilers, which most computers actually don't have. And you can't install them on clusters because they require root access. So running a container for StyleGAN3 is actually the best way to run that code. Okay, so that concludes the talk. Any questions? Yeah, so Docker itself is a very massive topic. This is just a high-level overview. Definitely look into it if you need to share the code.
Thanks to you. Do you recommend using this like on your local system,
Yes, in general, yes. I think you should always use Docker if time allows. So you might have a few extra hours of setup, but after that, you can trust that it always works.
So you always have the same environment you can just carry around with you, basically.
Yes.
Yeah.
Especially sharing the code with someone. I think when I was doing Scout and 3, I managed to share it with everyone, even though everyone has different setups. I just give them the Docker image and the command to create the container. It just
Great.
works everywhere on every cluster.
And Docker is free to use for personal use, I guess?
Yes.
Yeah, excellent. Setting up Docker for deep learning. So there's a question in chat for you.
I guess at some point I'm happy to, but yeah, it takes some time to set up because it does need to download a few gigabytes of stuff. But yeah, maybe at some point I can.
I have a question. Can I directly ask, or do I need to type in the chat?
Oh, you can ask. Yep, go ahead.
Thank you for the amazing presentation. So with the weights and biases, is it very easy to track the different versions of the model and which one's better? Does it store the weights and the location? How much tracking is allowed? And what are some of the tips that you would recommend for people who want to start using it?
So weights and biases, you can track as many as you want. It's almost infinite how much you can track. So you can just define, I'll just see if I can have the slides. Okay, so you can track multiple experiments by just having projects and different projects. Inside different projects, you have different runs as well. So I would recommend checking out that documentation. So there's a few parameters you can pass in to track different runs. You could even save weights, save source files, save training logs. Just anything that's savable can be tracked. And hyperparameters even.
Right, okay, thank you.
No worries. Yeah, sorry, there's a few things I didn't touch on quite much here, but yeah, it's on the documentation page.
Yep. If there's no more questions, we might move on to our next talk. Thanks to you for that. So our next speaker is Wei, and if Wei can come on and share his screen. All right, getting there.
Can you guys see the screen?
Yep. Looks good. Can see you as well. Yeah, go ahead whenever you're ready. Thanks, Wei.
All right, so hey everyone, my name is Wei. So thanks to you for the quick introduction to the weight and bias and Docker. So weight and bias is really good when you're trying to visualize the losses or visualize the output from your model, but it doesn't actually tell you what is actually happening during the model training, such as the resources that has been used by the model and so on. So today I'm just going to give a presentation about how you can optimize your model training by analyzing or profiling the deep learning models. So why do we need to optimize the model training? Well, there's a couple benefits. First, we can decrease the computational time during the experimental stage, which means we can reduce the cost for the trial and error, so you can do more experiments within the limited time. Second, we can also reduce the memory consumption of the model, so therefore we can fit more batches for faster computation, or we can make model with more complex structure. So in overall, it will release the hardware limitation issues. So before we talk more about how we can optimize the model training, let's have a quick peek on the improvement after the optimization. So this slide here shows some results for one of my model, which I just did. So you can see that before the optimization, my model used about 10 gigabytes of video RAM at the peak during the training. And the training speed is about 400 milliseconds per step, and the inference speed is about 60 milliseconds per step. But after the optimization, the exactly same model only used about 2 gigabytes of video RAM during the training. And its training time is much faster, which are like 200 milliseconds per step compared to 400 before. And its inference time is only about 40 milliseconds per step. So you can see that's a huge improvement by just doing some optimization outside the model itself. So how we can actually achieve such optimization? Well, before we can do any more optimization, we need to first analyze or understand what is actually happening during the model training. So the way we're going to do this is going to use a tool called the TensorBoard Profiler. So it's basically an API under the TensorBoard. So the TensorBoard Profiler is a tool to track the performance of the model training. It can check how model performs on different hardware, such as a CPU or GPU respectively. It can also monitor the computational cost of different TensorFlow operations, such as the consumed time or memory. So if you're using TensorFlow, the way you're going to enable the profiling is really simple. And if you're using keras.model.fit, all you need to do is to add a callback function called the TensorBoard. And if you're doing the custom training, all you need are these two lines here. So you can use the first line to enable the profiling any place you want. And you can use the second line here to stop the profiling any place you want. So I think there's an equivalent API in the PyTorch if you want to use it, but you can look into more details if you like. All right. So before we actually look into more details about how we can optimize the model training, let's just first, I'm just going to quickly show you a demo which I prepared for the presentation today. So here, and I will share this code later on in the Slack. So as we mentioned, what we're trying to do now is we're trying to monitor the model training using this profiler here. So if you look at this code here, so what this code does is basically I'm trying to run a segmentation task where the input for our deep learning model is an image for the brand, and the output is a segmentation map of that input image. So the segmentation map is basically the label maps where each pixel represents the classes of that pixel. So you can see here, let's just quickly go through the code here, see what I did within this code. So the first block here, of course, is just the import the libraries. And let's just give a run. And then the second step here is to set up an environment such as a parameter, or we create the folders for the output. And then what we have here is to load different kinds of inputs. So the way I load the inputs here is using an API from TensorFlow called the tf.data.dataset. So it's basically what happened here is first we'll load all the file names for our input dataset, and then we convert all the file names into the tf.data.dataset structure, and then we shuffle the input, and then the whole thing here is we create some functions to load the input image by using their file names, and the whole thing is done by using this map function to the data generator. And then we create this function here to visualize our input data set. So if we run the code here, so you can see that's the output here. So this is the input to our model. You can see this is the MRI brand image. It has different structure within the image. And this is the target output for our model, where every single pixel has been classified into different classes, and overall that will give us the segmentation map. Okay, so that's the input for our model. And then what's happening is we want to build the model we're going to use for the segmentation task. The way we're going to do is to use the network we're going to use for the segmentation task is the network called the UNet. So UNet is a very famous segmentation model that people has been used widely for the medical image. So it has three major sections. One is this encoding path. encoder, where you put the input image into the encoder, and the encoder will do some dimension reduction. And then at the bottom here, it will extract key features from our input image. And second is this decoder path, where you feed the key features into the decoder, and decoder will do some reconstruction and output the segmentation map, which is this one here at the output here. And the third part is this skip connection here. So the skip connection here will help the reconstruction process. So that's the overall structure of the unit. So you can see here, we're building our models for the unit. So you can see we have our input layers, we have the different convolution layer, max pooling layers. And so this whole section here is the encoder I was talking about. And then we also have the decoder here. So it has layers such as the upsampling, convolution, concatenation, and so on. So for all the convolution layer, we're using ReLU activation function to give this non-linearity. Yep, and we also have this last output layers here to output the segmentation map using an activation function, which is a softmax here because it is a multi-class segmentation task. So then we build our model using the carousel model with the input and output. Okay, so that's our model. Let's give a run. So you can see we have all the summary of the model here with different layers and different layers name. Okay, that's good. So then what I have here is I create the function to just show you the output of the model right now without any training. So if we run the model, run the code here, let's say it takes some time to initialize the TensorFlow. Okay, here we go. So you can see that's the input for the model. That's the target output that we are aiming for. And this is the output from our model right now. We can see because the model has not been trained yet. So the output here looks really strange, but that's all right. We're going to train the model later, make it better. Okay, now we have our model, we have our input data set. We want to train our model. So before the training, let's do some setup as well. So the first thing we have here is the training loss. So the training loss we're going to use for our model today is a categorical cross entropy loss. And because it's mainly used for the multi-class segmentation task. And as for the optimizer, when we're trying to optimize a model, we're going to use Atom. And then we have here is the training function. So one thing I forgot to mention is that we're going to train our model using a custom training loop instead of the model.fit. So, which is basically using this gradient tape during the training. So if you look at this function here, which is the main training function we're going to use during the training, you can see these 3 lines here basically represents the forward pass, where we pass the input into our model and get the output. So within the gradient tape, we have our model and we feed our input image into our model, and which give us the segmentation map. And then we compute the losses between the target label maps and the predicted segmentation map. And this gives us the segmentation loss. So all the operation will be recorded using the gradient tape. So this is the forward pass. Once we feed the model, or once we've done the forward pass, what we need to do is we want to do the backward pass through the backpropagation to update the weights of our model. And in the TensorFlow, it's pretty simple. All you need to do is first, you use the tape here, which is recorded, to calculate the gradient based on the losses and the trainable variables within the model. And then we want to apply these models to optimize the weights within the model by using our specified optimizer. So that's the whole training process during the model with the forward and backward process. And then here we have an actual function just for the validation. So you can see that within this function here, what we do is we take our model and we feed the input image into our model, which will give us the segmentation map. And then we calculate the validation loss based on the prediction here and the ground truth label here. Okay, so the last section here, what we have here is some TensorBoard operation where we try to store the losses and the image into the TensorBoard. So it's basically doing this exactly same thing as the weight and bias that you just mentioned, but just in the TensorBoard in our case. So you can use any approach you want, but this is optional. Yep. So as Shix mentioned, he already mentioned some of this in his crash course. If you want more details about the code here, you can probably go through the recording from last week. Okay, so now this whole thing here is the setup for the training. What we want to do next is actually do the real training for the model to make the model performs better. So you can see this is the very simple, this section here is used for the model training. So if first we want to validate how the performance of our model. So we want to record the time of the training time. So what we have here is first, we enable the profiling. Let's just mention here. So you see this code here is used to enable the profiling. So all we need to do is before the main training, we just enable the profiling. That's it. And then we have the for loop what we have here is basically the main training loop with number of the epochs here. So within each of the epochs, first thing what we do is this section here is a main training loop where we iteratively take the input from the data set structure we made. So basically we take some input and then we cast the input in this input image into a specific type that we're going to need. So in our case here, we're basically casting our image and label maps into this Keras variable D type, which is a float 32. And then we feed both our input image and label maps into our training function we just mentioned before here to do the training. And then we basically just store the losses and update the progress bar, which you're going to see later on. And then the second loop we have here is basically the validation loop. So we just loop through all the input from the validation data set. And then we do the exactly same thing. We cast the input into a specific data type, and then we feed into our validation training function, and we update the losses. So one thing I forgot to mention is you can see I'm using the test data set here. So normally it should be training data set. It just for the demonstration today, it is faster training. So you can change this later on if you want. And the last step here is basically just record all the losses value into the TensorBoard. You will see later on, just like the weight and bias stuff. Okay, so that's basically the whole training procedure. So the only thing you need to pay attention for today's presentation is these two lines here. So first, before the training, we enable the profiler to record what's happening during the model training. And after the training, we stop the profiling. So now let's just give a run. I think I'll run here to see how model performs right now. So if we run the main training loop, you can say start the running. It first start the profiling first, and let's just give some time for the model training. Okay, that's where it should be running now. Oh, okay, it's running now. Why is it so slow? Yeah, I think it's not using it. Feels like it's not using the GPU right now. Just give a quick restart. Let's see what's happening here. Okay, so while we're waiting for the whole thing is running, any question regarding to what we have so far? Like the question regarding to the code, the question regarding to the optimization.
I have a question.
Yep.
If you're using PyTorch, then what do you do for profiling?
Right, I'm not too sure about exactly the API you're going to use for the PyTorch, but I'm pretty sure there is the the way to do this? So Flix, do you know it? Because I don't use PyTorch a lot, but I think there's a way you can use a TensorBoard with the PyTorch during the training. But
Oh,
yeah,
okay. I'll check it out. Yep. Thanks.
Yeah, TensorBoard is usable pretty much with, yeah, you can use TensorBoard with PyTorch. Obviously the Keras callback stuff is all different, but I think I would expect the profiler parts to be the same.
Okay.
I haven't used TensorBoard with PyTorch myself, but I have seen many people use it. It's just a package, so yeah. I don't know if CU has a comment or knows anything about it.
all right. I don't know what's happening here, but it's really slow, but it's all right. We have some backup. That's what happens when you do the live demo sometimes. But yeah, so after you run, I'm just going to give a quick restart here. Okay, so let's just first have a look at backup I have here and see how's everything happening. Okay, anyway, let's just have a look at the backup I have here. So basically what I have here is once you finish running this whole thing here, it will output some results. And also we have some, we're going to have something like this one here. So just quickly show you. So that's the backup I have. So you're going to, because I create this TensorBoard folder to store all the TensorBoard record. So you can see we're going to have something like this. And all you need to do is to TensorBoard and log directory with this folder here. And then it will open up a backend API. So if you click this backend API here, it will bring you to the TensorBoard operation you have here. So you can see it's a bit messy right now because it has multiple versions here. But if you go to this section here and go to the profile, and you will be able to see the profiling during the model training. So what we have here, this one here is basically the results we're running with this file here. And so within the thing, you can see what happened here is a breakdown of what's happening during the model training. So you can see first we have here is a performance summary, where the most important thing here is the average step time. It's basically so within the code, you can see here during the training, we have different number of the steps for within each epoch. So the average step time here is just give you the average step time during the training. And you can see it's only 200 milliseconds right now. And there's something wrong with it. I will mention later. But if you look at the details into the breakdown of the step time, you can see first we have here is a kernel launch time. It's basically the CPU, it's the time that takes CPU to launch the kernel for all your convolution operation. Second, we have this device compute time here. And so what device mean here is basically means the GPU. So this here is basically the GPU computational time. So it tells you how much time it takes for GPU to run a computation within each of the step here. And then we have three important values here. So the first one here is called the TF operation placement. And within this thing, you can see we have two options. One is host, another one is device. So the host basically represents the CPU. and the device here represents the GPU. So you can see here about 98% of our operation, TensorFlow operation, are actually conducted on the CPU right now. And then only about 2% of the TensorFlow operation are conducted on the GPU, which is not desired. So that's something we want to optimize later on, because we want to put all the most operation into our GPU to utilize the parallel computing advantage of the GPU, therefore to accelerate the whole training time. And then what we have here is operational time spent on the eager execution. So you can see what happened here is we also have the CPU and GPU here. So for the eager execution, I will talk more later on. But for right now, all you need to understand is eager execution is a very computational expensive operation. So we want to avoid eager execution as much as possible to accelerate or increase the efficiency of the model training. But for right now, you can see the operation on the CPU have no eager execution. That's good. But the operation on the GPU right now is about 100% eager execution. So we want to reduce that later on. And then what we have here is the device compute precision. That's basically tells you the data type you're using for computation through the whole model training. So you can see we have 16 bits floating operation or 32 bits floating operation. So you can see for right now, every single computation we have in our model are under 32 floating operation. That's something we want to reduce as well, because as you know, 32 operation basically means more memory to store the data and longer computation time sometimes. Okay, so that's the whole overview of the model training. And within here, you can see that within our code, our setup epoch before, for this experiment here, my setup epoch is 2. So you can see we have two steps here. So each step represents one epoch here. So you can see that it has this breakdown. It's basically the visualization of all the information we have on the right side here. Okay, so that's the overview of the model training right now. And then what we need to look, it also have different tools to analyze the model training. The second thing we need to pay attention to is this kernel sets. Oh, sorry, not the kernel set, the memory profile here. So within the memory profile, you can see that it basically tells you, give you a summary of the memory consumption during the model training. So you can see in this table here, we basically have all the breakdown information. So first we have the memory capacity, which indicates the available memory from our system. Because I'm using the RTX 3090, so it has about 24 gigabytes of the video RAM, but only 22 available right now. And then the peak heap usage here basically represents the peak memory consumption by your model during the training. So you can see that for our model right now, the peak memory consumption is about 1.2 gigabytes of the video RAM. And then if you look at the memory breakdown table at the bottom here, you can see that it basically tells you the amount of memory consumed by different operation during your model training. So you can see that the top one we have here is the conv2D backpropagation. And it's basically, we have lots of the backpropagation operation here, which consume the most of the memory compared to the rest of the operation. But we also have the concatenation, ReLU, and so on. So that's the memory breakdown. And then we're going to look at it, it's a TensorFlow operation status. So within here, you can see it basically give you a pie chart of the time consumed by different operations during the training. So you can see on the device, which is our GPU, the most TensorFlow operation most time are consumed by this CUDN auto tuning. It's basically used for all those TensorFlow operation, like the convolution and so on. And then on the CPU, what we have here is you can see most of the time are consumed by the read file. That's basically when you load the data set using the tf.dataset one. And then we also have this decode PNG. So remember within the code at top here, we have this function to decode the PNG. It's basically loading the PNG file from the file names. So that's what's happening, taking time here. And then we also have the equal and casting and so on. So you can see it's give you a really clear breakdown of which part of the operation during your model training are consumed most time. And then the most important thing about this profiler is actually this trace viewer. So if you look at the trace viewer here, what it does, it looks pretty messy right now, but it's actually pretty simple to understand what's happening. It's basically give you a step-by-step analyzing or breakdown for the model training procedure. So you can see, let's look first, have an overview. So the top section here is for the GPU. That basically means all the operation running under the GPU. And the bottom here is basically all the operation running on the CPU. So if you compare the color blocks between the top and bottom here, we can clearly see most of the operation are actually running on the CPU right now, which is why it's like super slow running. You can say it's still running the model here, but I think it's, yeah, you can see it's really slow. And then if we look into what's happening in the middle here, so if you look at the structure here, you can see we have similar patterns within each of this block here. So that's basically a single step during the training. And if we zoom in a little bit from the start, which is here, you can see what we have here. So you can see within the CPU right now, we have this eager execution, which I'm going to talk more later on. It has convolution 2D. It has adding the bias. It has redo function. It also have another max pooling. You see that? It is exactly the model structure we're defining here. Within the structure here, you see the convolution, max pooling, leak value. So that's exactly what's showing in this graph here. So if you look at the operation within the GPU, you can see it doesn't have much operation right now. The only thing it does is this convolution operation. So right now, everything is actually conducted in the CPU. Only the computational expensive operation or matrix operation like the convolution is actually running in the GPU right now. Okay, so now if we go back to the overview, you can see that there's lots of improvement we can done on the model right now. So let's stop this one for the while. Okay, so normally when you run this model, I'm not sure what's happening right now. Maybe something wrong with my system, but normally for this code right now, the running time for the whole training procedure should be around 12 seconds. Okay, so now let's go back to the slide here. So now we have the profiler. We know what is the profiler and how we can know what's happening within the training procedure using the profiler. We want to optimize the performance of our model training. So how we can do it? Well, there are basically three ways you can do it. First, we can reduce the percentage of operation executed in the eager mode, which is exactly the one we're talking about before. You see right now, 100% of the operation in the GPU is actually running under the eager mode, eager execution. And second approach to optimize the training is to increase the percentage of the operation placed on the devices versus host. Remember, devices is the GPU, host is the CPU. So you can see here, for right now, most of our operation are actually placed on the CPU. So we want to decrease this number, and increase this number here. And the last thing we want to do is we want to use float 16 data type instead of float 32 for some of the operation during the model training. You can see right now, every single operation is running in 32 float number. So we want to reduce this number and increase this number. So let's do this. Let's just talk about each of them individually. So the first thing I also mentioned is we want to reduce the operation in the eager mode using the tf function. So what is the eager mode? Eager mode is also called eager execution. Basically means the TensorFlow operation are executed by the Python interpreter. So if you have a function if you have functions with multiple lines of the code, the whole function will be run line by line, and then it will return results immediately back to Python after each of the computation. So you know the results immediately after the computation. So it is really good for debugging and quick checking of the results. However, as I mentioned before, it is operation with a very high computational cost. So what TensorFlow does it uses something called the graph execution. So that the graph execution basically means all the TensorFlow operations are executed by building a graph of them, which is shown on the right here. So you can see within this graph, we have all the major computation operation, like the matrix multiplication, the addition, and so on. And we also have this arrow that indicates the flow of the signal. So you can see we have some output from another operation, and we feed it into this matrix multiplication, and we add some bias here, and so on. So you can see all the TensorFlow operations are actually represented in this graph form. So why we want to build a graph? Well, the graph can be saved, run, or restored without the original Python code. So if you lost your Python code, but you still have this graph, the TensorFlow can still run it. Second, the graph can be used in the environment without the Python interpreter, such as the mobile or backend services, and so on. And at last, the graph is also easy for optimization for more efficient computation. So how do we generate a graph? Well, in the TensorFlow, all you need to do is use the function called the tf.function. So there are two ways you can do it. The first way is using a direct call. So let's say we have a function here. All you need to do is to use this tf function with the name of the function here, and that will give you a graph version of that function we have here. And the second way is that when you define the function, or you can use the decorator, which is at tf.function. So that will automatically make this function as a graph. All right. So what's the advantage of the graph here? So the tf function, or in other words, the graph we just made, can bring huge improvement for lots of small computation. An example is shown on the right here. You can see what we have here is a power. It's a sequence of the power operation. So if we compare the results for the function, and after applying the tf.function to the function, we can see that the time difference is huge. So without the tf.function, it takes about 2.4 seconds to run the whole operation. But after we apply the tf.function, it only takes about 0.6 or 0.7 seconds. So one important note for the tf function is that the tf function must return values. So you can within the function. So that basically means you cannot directly access any tensor or values within the function except through the return values. So that's also make it impossible to use recursive function with the tf.function. Okay, so now we understand what the tf function is. Let's give a try to our demo here. So to enable the tf.function, all we need to do, as I mentioned before, is to implement this tf.function for the function that we want to make the graph for. So if you look at here, because the main thing is to build the TensorFlow operation. So we want to you only use the tf.function at a place where we have lots of TensorFlow operation. So within our code, we have two places we use lots of TensorFlow operation. First is the training function. So all we need to do is to wrap the function with the tf.function API here. Another thing is we want to make the validation function as a graph as well. So all we need to do is the tf.function with the validation function. Okay, so that's all you need to do. So you're basically converting all the intensive TensorFlow operation into a graph now. So now if we run the whole thing again, so a function question here. That's hopefully is what we're running this time, but yeah, I think it's messing up again, but anyway. All right, so if you go back to our TensorFlow here, so you can see that the second one here is we enable the tf.graph. This is the basic results after you enable it. So you can see now the average stepping time is 16.4 milliseconds. You can say, well, after enabling the tf.function, why this time is even larger than before? Because before we only have 2.8 milliseconds. Because that is because the time we have here is only recorded with the graph. So before we don't have any graph, so the whole time is not recorded there. But now, after using the TF function, the whole procedure is actually recording within the TensorBoard. So if you pay attention to here, which is most importantly, you can see that after implementing the TF function, if you look at the percentage of the TensorFlow operation within the CPU or the GPU, you can see that now it's about 60% operation on the CPU, but 40% operation on the GPU. So this is exactly the same code before. The only difference is the TF function. You can see we successfully reduced this operation on the CPU, but increase the number of on the GPU. And now if you look at section parameter here, remember before, the operation on the GPU is about 100% eager execution, but now it's only 0%. So which means we get rid of all the eager execution. And then it's probably not very intuitive here, but if I could run the model, you can see that after running the model before, without the TF function, it takes about 11 seconds to run the whole training procedure. But after you run it, after you use the TF function, it not only uses about 9 seconds. Okay, so now if you go to the TensorFlow, back to the tracer view here, and if you compare this graph here with the training procedure without the TF function. So remember, this is the view, the tracer view before we implementing TF function, and this is after implementing. You can see we now have more operation within the GPU. So if you look into what's happening here, you can see this is the number of each epoch here. So basically, that's the training epoch for the whole training procedure. And now if you look at the details of what's happening, you can see first we have this convolution 2D, and then we have max pooling. So conv2D, max pooling, conv2D, max pooling, and so on. So that's basically the structure we just defined using the unit. And this whole section here, so if you look at this whole section here, that's basically the forward pass we mentioned before. And then what we have here is a backward pass. You can see all the gradient tape. So within the gradient tape, what we have here is we have the convolution, and upsampling. You see here? Oh no, convolution, probably upsampling later on. Convolution, and concatenation upsampling here. So you can see that this whole thing is actually the reverse process of the model. So this whole section here is basically the reverse backpropagation process. And then at the very end here, we have our atom. So that's the optimizer we've chosen. So this is basically where we update the weights of our model. So you can clearly see that after implementing the TF function, most of the operation has been moved into the GPU. That's what makes the training much faster than before. Okay, so that's the TF function. So one thing about TF function you need to pay attention to is something called tracing and ray tracing. So what the tracing does is it basically means the procedure when you capture the TensorFlow operation into the graph. So during the tracing procedure, let's say we have a function here. We will run the function code line by line first, and then for all the TensorFlow operation. So in this function here, this is a TensorFlow operation because A here is a tensor. So we're basically adding two tensors together. So for the TensorFlow operation, a graph will be built with no direct computation. But for the standard Python operation, such as the print function here, so the print function here is not TensorFlow operation. It is just a standard Python operation. This print function will not be captured in the graph. So this function here will only run once during the tracing of this function. And so once the tracing is done, so we have the graph already, this Python function will not be run anymore. So an example is here. So if we run this function for the first time by inputting tf.constant with a string value, you can see that the output here will be first, the output from this Python operation print function, which is basically traced with the tensor, and then it will also output the output results from is a plus a here. And then if we run the same function again with exactly same input, but just different string here, you can see that we don't have this output from this print function, because after this procedure, the graph has been built. And when you run this function again using a similar input, it will directly use the graph to do the computation, and this print function will be ignored. However, what happened here is that if you feed an input with different data type, so for this case here, it is still a constant tensor, but the value inside this constant tensor is actually an integer instead of the string. You can see what's happening here is it's basically running this print function again. That means the whole function has been traced again. That's what we call the ray tracing. And the reason causing this is because our input now have different data type. So things you need to pay attention here is that it's good to build a graph for each of the function here because it has much faster computation. But when the data type and the dimension or shapes of input change, it can also cause ray tracing, which means it will build a second graph for the exactly same function. And this ray tracing process is very expensive and need to be avoided. So how can we avoid this ray tracing process? Well, there are three main ways. First, you can specify in the input data type for your function. So if you have a different, when you input a different input to that function, it will raise an error message. Second, we can specify the input shape as unknown. So in this case, your input can have different dimension without doing this ray tracing procedure. And the most simple and direct way is to actually pass a tensor instead of the Python arguments into your function here. So an example is shown on the right here. You can see within this function, we'll basically do the training. And the input for our function, train function here, is number of the steps here. So within this function, we have two different print functions. One is a Python operation print, another is a TensorFlow operation print. So when you build the graph, the second print function will be recorded inside the graph, but the first function will not. And then if we run the code here, you can see when we run the code with different input here, so you can see the input here right now is a Python input. So we have number of the step, which is equal to 10. We also have a number of step equal to 20. So if you look at output for these two functions, you can see that this Python operation, which is tracing with number of steps, are run twice for them. So that's called ray tracing. We want to avoid that. So what we need to do is we convert this input into a TensorFlow constant, which convert it into a tensor. And then we feed the exactly same thing, but in tensor format into this function. We can see the second time when we run it, it no longer have this tracing problem. So that's how we avoid the ray tracing when we build the graph. Okay, so that's enough for the tf function. So you can see that we can use tf function to build a graph of the computation, therefore increase the training speed. And then the next thing we need to do, remember as before, we mentioned before here, we also have this last part here, where we have this data type for the computation. So what we want to do is we want to decrease the 32 bits floating operation and increase the 16 bits floating operation. So the way we do it is use something called the mixed precision 16 bits. So within this, so what is the mixed precision 16 bits? It basically means we use both 16 bits and 32 bits floating operation as during the whole model training. So why we want to use 16 bits? Well, the 16 bits use less memory, and it can also run faster. So especially for the modern GPU, they have this specific architecture that can accelerate the 16 bits operation. But why do we want to keep 32 bits operation? Well, because the 32 bits have better the numeric stability, and it also will make the model have lower step time, because remember, when you're converting from the 32 bits to 16 bits, it will take time to to change the data type of the variable. And lastly, the 32 bits can also preserve the accuracy as much as possible compared to the fully 32 bits operation. And so the way we achieve this is using the mixed data type during the whole computation. So basically, that means we're going to use the float 16 bits for all the computation. which means the variable will be cast to 16 bits before the computation, such as the matrix multiplication and convolution. And for the 32 bits, we're going to use the float 32 bits for all the trainable variables. So that basically means the variable will be kept into 32 bits when storing the computed results, such as the trainable weights within the kernel. They'll be kept as the 32 bits. So one special case for the mixed precision is that any activation function or layer at end of the model that does not have any trainable parameters will also be converted to the float 16 bits if you enable this mixed precision. So that's why we want to manually change those those layers into 32 bits, because we want to make sure that the output of our model are always in 32 bits for the stability issues. So let's have a look at how we can implement this mixed precision into our demo here. So all you need to do is you have to enable the mixed precision. If you look at the code here, so the first thing you want to do when they enable the mixed precision is this one here. Want to set up an environment. So when we enable the mixed precision, all we need to do is this two line here. So it's basically the chars.mixedprecision.policy. We give that parameter called the mixed float 16. That's basically the mixed precision we're talking about. So both float 16 and float 32 will be used during the computation. And then we set up the global policy with this new policy here. So now if we check the policy computation output, you can see that we have this compute data type and variable data type. So once you set up the mixed float 16, the compute data type here will be 16 bits floating point, and variable data type here will be 32 bits floating point. And then what we need to do is the mixed precision here is to use the loss scaler. So what does this mean? So one problem when you implement the mixed precision 16 bits in the custom training is the underflow and overflow. So what that means is that if the value of the variable is larger than this value, it will over the range of the maximum value of the 16 bits. That will cause the overflow. So when overflow happens, the value will become infinity. And for the underflow, that basically means the value inside the variable will be lower than this value. So when underflow happens, the value will become 0. So that will cause a problem for the model training, because if the value and smaller than this value becomes 0, that basically means your gradient will become 0 and your model will stop training. So the solution for this is to avoid this underflow or overflow. The solution for this is the loss scaling. So what does loss scaling mean? Is that once we're going to create a loss scaler to scale the losses. And then what happened here is once we compute the losses within the gradient tape, we will multiply this loss value by a large number, such as 1024. And then this gradient will also be scaled up to 1024. So and then we'll use this scaled loss during the gradient. We calculate the gradient. And then that means we will have a scaled version of the gradient. So, and then before we apply this gradient to update the weights for our model, we will scale the gradient down again by dividing them by 1024. That's what I call a scaling procedure. So you can see 3 major components here. We have here, first, we're going to create a scaler. Second, we're going to scale our losses by a large number. And then after computing the gradient, we will unscale the gradient. So that's exactly happened in our code here. So you can see what I did here is first, I create a loss scaler for the optimizer. And then what I did here is once I calculate the segmentation loss during the training function, I will scale the losses by time a large number. And then during the backward process, what I'm going to do is instead of directly calculating the gradient using our losses, we're going to calculate the gradient using the scaled loss, scale loss, and then unscale the gradient. We'll use this gradient to update our model. So that's the whole procedure for the mixed precision. Yep. So once you run this whole code, I also have the TensorFlow operation here So that basically means we enable the TF function, we also enable the mixed precision here. So if you look at the overview page here, you can see that once we enable the mixed precision, you can see now the average step time is only 15 milliseconds. If you compare this to the before is 60 milliseconds, not a much improvement. But that's because the TensorFlow operation we have in this code here is very small. So if you're going to have a very large model with lots of TensorFlow operation, by doing this mixed precision will significantly improve your computational time. And now if we check this parameter here, we can see that now about 60% of operation are actually running in 16 bits, and only 40% are running in 32 bits. If you compare before, you can say before is 100% 32 bits. So now we successfully increased the number of the operation using 16 bits. Okay, so if we run the trace reviewer, I think the only thing you're going to see in this trace reviewer, you can see there's still a large operation happening in the GPU. But because we have this data type conversion between 16 bits and 32 bits, there will be lots of operation as a casting operation because we want to cast them between these two data types. Okay, so as I mentioned before, there are some problems with the mixed precision. So you want to use this very carefully. So in my opinion, you probably only want to use this during your experimental stage, because by changing the data type from 32 bits to 16 bits, you're definitely going to have lower accuracy. But sometimes the accuracy is very small, but still you want to avoid that. And also it has this underflow and overflow problem. So that's something you need to take care of during the training as well. So in conclusion, what happened during my presentation today is first, I give a really quick tour to the TensorFlow profiler. So how we can use this profiler here to analyze the model training performance. Second, we have a look at this trace reviewer to show us what is exactly happening in our model training step by step. Third, we successfully minimize the operation executed in the eager mode using TF function, hence improving the computation speed. And at last, we learn how to enable the mixed precision 16 bits policy for faster model training. But remember, use this one with a caution. Okay, so that's pretty much for my presentation today. So any question regarding to the whole procedure here?
Thank you, Wei. That was very informative and very thorough. I appreciate the time you've taken to put into all of these things. Now, questions for Wei? I know some aspects were very TensorFlow oriented, so I put stuff in chat.
So one question I do have, that was a very comprehensive and very detailed. Thank you so much. So what is the one thing, if you would recommend that what's the first thing you look at when you're profiling your model, always get that right? What would that be?
Okay, I think the first thing you need to look at once you're done the profiling is definitely, let's just use this one. It's definitely the overview page here. So because within the overview page, that's something you need to pay attention to. Because firstly, as I mentioned before, you want most of your operation running on the GPU, which is a device here. So once you run your model, if in this case here, you can see we only have 2% of the computation running on the GPU. So that's something I need to fix. And second thing you want to fix is that you want to avoid eager execution for your final product. Because during the experimental stage, it's all right to have eager execution because you want to check. During the debugging stage, it's all right to have this eager execution because the eager execution can give you immediate results when you run a TensorFlow operation. But once you start to train your model with different data set or different parameters, you want to avoid this eager execution by reducing this number here. And the way you do it is to use the TF function, as I mentioned before. And then the second thing you want to pay attention to is probably the memory profiler, because one problem for the deep learning training is that it's very memory hungry. So you're always going to have this hardware limitation when you're going to train your model with a large data set. So if you pay attention to this, once I do this mixed precision and with memory profiler, you can see that I can basically look at, if you have this, like the all of memory issues, this is where you want to look at it. So you want to look at which operation is actually taking a large portion of your memory during the training. So you can, in my case, it's backpropagation, and there's nothing I can do about it because backpropagation is pretty much required for your training of the model. But in some case, based on my experience, you're going to see some operation that are going to consume a large amount of memory, which you can reduce them by using TF-dot function or mixed precision and so on. And the last thing you want to see is this trace reviewer. So if you want to see what's actually happening in your model, like say, because this is all in time scale. So this horizontal line is a time. So if your model is running really slow and you want to know what's happening, this is some place you want to look at. So that's basically the three things I would recommend to look at using the profiling.
Thank you.
Yeah, there's a question in chat.
Yeah, could you give a quick definition of the graph from an interpreted language perspective? Okay, so I'm not a programming background, but so I will try my best to explain what the graph is. So basically, like when in your Python, you have when you run the code, the whole thing will be pushed to the Python. So the Python will, as an interpreter, will interpret your code line by line and run them line by line. But when you build the graph, what happened is it's not going to compute the values the first time you run the code. It will build the graph of that function without giving out any output. So the whole computation will only happen when you run the code again, when you use that function in another, like let's say your main training loops. So in that case, the TensorFlow will not look at the code you have there, but it will have a look at the graph you have there. So it will directly using the graph to do the computation. So that's what makes the graph much faster. Does that make sense? Sorry, that's probably the thing I can say about the graph there. So it's basically just skipping the whole interpreting stuff. It's just running the graph. It's like the Lego module. Once you build it, it's just going to use that module straight away without even looking at the code. I hope that answers your question.
So the way I thought of it was like G programming, the kind of thing that's implemented in LabVIEW and things like that, where you need the output of one thing before you can run the next thing, and so it becomes a single sort of block rather than passing arguments and getting a return value for each sub thing. You sort of chain it all together and just and run it as a lump. But I don't know. That's just my impression as you were talking.
Yeah, I think that's a similar idea. So you basically just by ignoring the code, you basically just you have a graph. That's the output. That's the input. That's the output. So when you have a graph there, it basically just feed the value into the graph. So that's why I have this ray tracing there. Remember the tracing and the ray tracing. So once you have a graph there, it's going to have multiple graphs for different input data types. So it will have a look at your input and match the data type to the graph you just built there. So it was straightway only feeding the input to the whole graph, and the whole computation inside the graph is actually done automatically without the code there. Sorry, does that make sense? Sorry.
Yeah, so TensorBoard can actually display the graph. I'm not sure if you got that enabled.
Oh, no, I haven't. I do have a code there, but I didn't enable this. So this is the graph page you have there. So yeah, once you've done the graph, it's basically just going to show you there. You can see
that's the graph there.
Yeah. So basically what happening here is, let's say in my code here, I have both two functions, the training function and the validation function, remember? So what happened here is I actually built two graphs, one graph for my training function, one graph for my validation function. And they will all look something like this here. So it's basically just telling you the exact operation and the flow of the signal inside the graph. And it's going to be treated as a whole modulus during the computation.
Yeah, so you can think of it as your Python script actually sets up the computational graph. Python script doesn't actually run the learning or training. Obviously, it may run other stuff, but your Python script is designed to create the graph and then run the graph. Great, thanks. Any other questions? If not, I think we'll call the end to the session there. Thanks again, Wei, for your very in-depth presentation. I think it's very useful even for myself. I'll be very keen on using like the profiling visualizer especially. And I hope you all found it useful. The recording I'll put up on Slack as usual. And yeah, thank you very much for attending, and we'll catch you next time. Actually, that'll be, I don't know, about an hour and a half, and I'll go through all the different types of deep learning models there are. And we'll see you then. Thanks again. Bye.